Hello, and welcome to Lecture 5 of the Forces unit in Phys 1104. In the previous video lecture, we were looking at the relatively simple case of objects with constant forces acting on them. In this video lecture, we're going to look at two slightly more complicated situations. One is where we have variable forces, and the other is where we have multiple objects all interacting via forces. Many forces are constant. For example, the gravitational force is constant. Often frictional forces are, and many other forces are or can be constant, such as thrust by rockets and jets. Constant forces are easy to deal with because they cause constant accelerations, and in Unit 3 of the course we learned good ways to find the subsequent motion of an object if we know that it has a constant acceleration. Many, or in fact most, forces are non-constant, however. We've seen that spring forces depend on spring length. We know that the accelerations during collisions are very time-dependent, and so they must be caused by very time-dependent forces. Air drag depends on speed. Electric forces depend on the relative positions of charges, and magnetic forces are very complicated depending on both position and velocity. But we'll see all of that in Phys 1204. The point is that predicting motions of objects when the forces on them are non-constant requires more sophisticated methods. We saw some of that in Unit 3, where we learned to integrate acceleration versus time functions. But as you may appreciate, that's rather laborious, and it would be nice to have some easier ways. So how does the spring deformation depend on the force exerted by the spring? Well, now that we know how to calculate gravitational forces from the previous lecture, we can use that to indirectly measure spring forces. If we hang something like a brick off of the end, then we know in equilibrium the upward force exerted by the spring is equal in magnitude to the downward gravitational force. And we know how to calculate that gravitational force, and so that's just given us an indirect measurement of the force that the spring is exerting on the brick, which is again equal in magnitude to the force that the brick is exerting on the spring. And so now we can do an experiment to find the function connecting the spring deformation to the force exerted. I'm going to set an x-axis along the spring, and that's just so that the x-component of our force and the x-component of the displacement of the end of the spring have signs associated with them that we can use to talk about direction. So we hang some mass off of the spring and see how much it stretches, and hang some more mass off of the spring and see how much more it stretches, and now we plot the x-component of its displacement versus the x-component of the force exerted on it, and we see that it's a lovely straight line. That's great. Linear functions are really easy to deal with. Now remember that the amount of deformation for a given force depends on how stiff the spring is, so we should probably repeat the experiment with a stiffer spring, and we again get a linear relationship, but we see a smaller amount of deformation for any given force. But I've been plotting that with the forces on the horizontal axis. That's because the forces were under my direct control, and so it made sense to think of them as the independent variable. But we usually plot these with the force on the vertical axis for reasons that you'll see. But part of this just shows you that what we choose as our independent and dependent variables is often sort of arbitrary. So plotting it up that way, it looks like this, with the stiffer spring having a steeper slope on the force versus displacement graph. And now we calculate the slopes, and they come out like this. Now we can write the force as a function of the amount of deformation, and because the data shows us this is a linear relationship, that's a very easy function to write down. The force is just some constant times the displacement of the end. And that constant is just the slope of our fx versus x graph. And we'll call that the stiffness of the spring. You'll often see it called the spring constant, but I prefer to call it the stiffness because that's more descriptive of what it means. And so if you look, we see that our stiffer spring has come out with a higher stiffness than our soft spring. That makes sense, and that's part of why we put the force on the vertical axis. Now, the force that the spring exerts on the mass is just the negative of the force that the mass is exerting on the spring. Remember, that means that these forces are the same magnitude and point in opposite directions. And so, in particular, its x component is going to be a negative k times the x component of the displacement. That negative sign is simply saying that the force exerted by the spring points in the opposite direction to the displacement. And either of these forms of the equation are what we call Hooke's law. Remember that with the choice of axes I made, positive values of the displacement of the end of the spring corresponded to stretches. Negative values would correspond to compression, and the springs I was using were too floppy to put them in compression, but I could use other springs and see that the linear relationship between the force on the spring and the displacement of its end continues into compression. However, Hooke's law is not universal. You can push things too far and things deviate from the straight line. That is what Hooke's law says. For example, if you compress too much, eventually the coils start getting in each other's way, and the spring does what's called bottoming out, and now a very large increase in the force leads to a very small change in the displacement of the end. At the other end of things, if you stretch it too much, then it starts irreversibly deforming, and as it does so, the f versus x graph becomes nonlinear. Eventually, the spring breaks. Hooke's law says nothing about any of this. It only applies in this linear portion that we call the elastic range. Let's check your understanding of forces exerted by springs. So here we have a spring which is 15 centimeters long when it's relaxed, and I've given you its stiffness, and at some moment it's stretched to a length of 20 centimeters. So what is the magnitude of the force exerted by the spring at that moment?